Very good afternoon all. I am DEEPA, working as assistant professor from EC department in Tigala Krishna Reddy Engineering College. Now I will explain error detection techniques in computer networks. Every network must able to transfer of data from one device to the another with complete accuracy. Okay, in the way of transmission of data from one device to another device, data may be corrupted. Okay, for reliable communications, errors must be detected and corrected. Okay, in any network, for reliable communication, each and every errors can be detected and corrected. Error detection and correction are implemented either at data link layer or transport layer in OSI model. Before going to the error detection technique, first we have to see what are the types of errors. Totally we are having three types of errors. First one is a single bit error, multiple bit error and burst errors. Okay, now see one by one. First one we have the single bit error. Okay. Here we have the sent and received frame is there. Okay. In frame, any one of bit is changed from 0 to 1 or 1 to 0. Only one bit at a time in a frame is changed from 0 to 1 or 1 to 0. That error is represented as a single bit error. Only one bit is changed in between sent frame and received frame. Okay, this is a single bit error. Coming to the this one, single bit errors are mostly this is type of errors in serial data transmission. Okay, the noise must have the very short duration, which is very rare. Okay, however, this kind of errors can happen in parallel transmission also. Next error is the burst error. Okay, here sent and received represents the frames. Okay, in sent frame and received frame, here two or more consecutive bits are changed from 0 to 1 or 1 to 0. That error is represented as a burst error. Okay. Here, two or more bits in data unit have changed from 1 to 0 or 0 to 1. Okay. Burst error does not necessarily mean that errors occur in consecutive bits. Okay. Length of the burst bit is measured from the first corrupted bit to the last corrupted bit. Some bits in between may not have been corrupted. Okay. Next one, we have the multiple bits. Multiple bit errors. Okay. In these type of errors, in between sent and received frames, two non-consecutive bits are changed from 1 to 0 and 0 to 1. In case of multiple bit errors, two bits are changed in sent frame and comparison of sent and received frame. Okay. These two bits are non-consecutive bits. Okay. This one shows the multiple bit errors. The burst errors is most likely to happen in serial transmission since the duration of noise is normally longer than the duration of a bit. The number of bits affected depends upon the data rate and duration of the noise. Okay. Here some examples are mentioned. If data is sent at the rate of 1 kilobyte per second, then noise of 1 by 100 seconds can affect 10 bits. Now see what is mean by error detection. Okay. Error detection means to decide whether the received data is correct or not without having a copy of original message. Okay. With the help of error detection, we can verify the received frame, but we do not have the original message. Original message is nothing but the sent field. Okay. Error detection uses the concept of redundancy. Redundancy. With the help of this redundancy only, we can calculate the errors. Okay. Redundancy is nothing but adding of extra bits for detecting the errors at the destination. So with the help of redundancy concept only, we can detect the errors in the received frame at the destination. Here, this picture shows the redundancy. Okay, in this one, first we have the data. Okay, this data along with redundancy, we can send from sender to the receiver. Now see here, this one, this yellow box represents the redundancy check. Redundancy is nothing but we are adding some extra bits. Along with redundancy, along with data, we can send the redundancy bits also from sender to the receiver. Okay. Here, we have to verify either function is correct or wrong. Okay. Here we have the term is a parity bit. Bit is nothing but we are adding extra bit. We are having two types of parity bits are there. First one is the even parity. Second one is the odd parity. Okay. Depending on that, we have to verify. Okay. With the help of redundancy, if any error is occurred at the receiver side without any original image copy. Okay. Now, we have to see types of error detection methods. Okay. With the help of redundancy, we can detect the errors at the receiver side. We are having totally 4 detection methods. First one is the VRC, second one is the LRC, third one is the CRC, and fourth one is the checksum method. We have to see these 4 error detection methods one by one. First one is the VRC technique. This is the error detection technique. VRC is nothing but vertical redundancy check. Okay. Here, first we have the data. The data is 11000001. Okay. Along with data, we have to add one more extra bit. Only one bit. Okay, that is the VRC bit here. Here, in this data, how many numbers of ones are presented? Only 3 ones are there. Okay. Here, we are utilizing even parity generator. Okay, even parity generator is nothing but if data contains the number of ones are even, that it will be accepted. That is even parity. Otherwise, it will be odd parity. Okay, if data contains the odd number of ones, that will represented as a odd parity. If number of ones in data is even, that will represent the even parity. Okay. Now, in this data, we are having totally 3 number of ones. For even parity, we can add one more one. Then only the data become even parity. That's the reason we are adding one bit as one in the VRC. Okay. Now along with this extra bit or VRC, we can send the data to the checking function. Okay. Here it verify either here number of ones are even or odd. Okay. If it is even, receiver acts. There is no error at the receiver. But with the help of VRC technique, we can detect only single bit errors. Okay, it can detect burst errors only if the total number of errors are odd. Okay, if errors are even, we can identify only single bit error with the help of VRC technique. If number of errors are odd, we can detect the burst errors also with the help of VRC technique. Vertically redundancy check. This is the first error detection technique. In this technique, we can add one extra bit to the data Okay. For even, generally we consider the even parity. For getting even parity, we can check the data. In data, we can have number of ones or odd. We can add the one VRC bit. Otherwise, we can add the 0. Next one is the longitudinal redundancy check, LRC, error detection technique. In this error detection technique, we can arrange the data in tabular form. Okay. We are having the data as 4 parts. Okay. Here, each and every, here this one arrow marks is represents the direction of movement. Okay. In this one for even parity, first we have to consider the all the first bits. Okay. In this first one we have the 1, next one, first LSB bit is also 1, here also 1. Totally in the data contains the total LSB bits are 4. So for even parity, that LSB bit in LRC is the 0. Okay. Next we have to check from the LSB. Next bit is the 1. Second LSB bit is the 1. Second data unit also 0. Next one 0. Next one 0. Means 1, 0, 0, 0. So total number of ones in data are only 1. For even parity, we can add 1 in the second LSB bit in LRC. Okay. Like that, we can add the LRC bits. LRC increases the detection of burst errors compared to the VRC technique. But we have the one disadvantage with the longitudinal redundancy check error detection method, that is, if 2 bits in one data units are damaged and 2 bits in exactly same positions in another data unit also damaged. Okay. If 2 bits in data units are damaged and 2 bits in exactly the same position in another data unit is also damaged, the LRC checker will not detect any error. This is the drawback in the LRC technique. This one shows the VRC and LRC. Okay. Vertical redundancy check and longitudinal redundancy check. Direction of transfer of data. Okay. This one LRC is the directional, longitudinally direction of transfer of whole block. Okay, in this direction. Okay. This one is represents the VRC. Okay. Vertical redundancy check. Okay. This one represents the direction of transfer of data with LRC and VRC techniques. Next error detection technique is a cyclic redundancy check, CRC method. This is very important error detection technique. Okay. In this one here we have the sender and receiver. First we have to see the at sender side. In this one, first we have the data. Okay. For this data, first we have to check the how many bits of divisor is there. Okay. Here we have the divisor bits are the n+1 bits. Okay. We put the data. After that, first we have to check the divisor bits. Here, totally we are having how many divisor bits? n+1 divisor bits. For any n+1 divisor bits, we must choose the CRC bit as n bits. For n+1 divisor bits, we must choose the CRC bits as n bits only. Okay. First, initially, we take the data plus n bits of data along with n bits of zeros. Okay. Here, n bits will be decided by the number of bits presented in the n+1 bits. Number of bits presented in the divisor. If divisor contains n bits, then we choose the n-1 bit along with data. Okay. In CRC bits, depending upon the divisor bits. If divisor contains n plus 1 bits, then we choose the CRC bits are n bits. Okay, this is at the sender side. Now, sender send the data along with CRC to the receiver. Okay, here receiver perform the binary division method for the data as well as the CRC. If remainder is 0, the data is accepted. If non-zero, that will be rejected. This is the CRC method. Okay. Previously, we are seeing two types of detection methods, VRC and LRC detection methods. Those two follows the binary addition. Okay. Coming to here, the CRC method follows the binary division. Okay. In this one, the main important thing is we have to choose the CRC bit that will be depending upon the number of bits presented in the divisor. If divisor contains n plus 1 bits, we choose the n bits in CRC at the sender side. Okay. If divisor contains n bits, we choose the CRC bits as n minus 1 bits at the sender side. Okay. After choosing the CRC bits, along with CRC and data, we can send from sender to the receiver. After performing the binary division, we are getting remainder. Okay, if remainder is 0, data will be accepted. Okay, if remainder is non-zero, data will be rejected at the receiver side. Okay, now see the CRC method with an example. Now, a k-bit frame or message, the transmitter generates the n-bit sequence. Okay, this one is known as a frame check sequence. So that resulting frame consisting of k plus n bits is exactly divisible by the some predetermined number. The receiver then divides the incoming frame by same number. If there is a no remainder, assume that there was an error. Okay, now see one example. Here we have the divisor. Divisor is 1101 and data is 1000100. This one is divided by the divisor as 1101. Now, total number of bits in this divisor is 4. So, how many bits in the CRC? Just we can add only 3 bits in CRC. Initially, we can add 3 zeros to the data. Okay. After adding the 3 bits to the data, why we are choosing here 3 zeros? That is only the thing. Here divisor contains 4 bits. Okay. For this condition, CRC bits are 3. Initially, we choose all the CRC bits are 0. Okay. Here with the divisor, we can perform the binary division. Okay. We can follow the binary division for this one. Okay. After performing the binary division, here see, quotient is 1101. First we have to do with 1. Okay. 1101. Okay. Here 1 minus 1, 0. 0, 0, 0. 0 minus 1, 1. 1, 1, 0. Okay. Next we take one more bit, 0. Again we have the 4 bits. Take. Here first bit is the 1. Depending upon the first bit, here you have to quotient is 1 or 0. Okay. If first bit is 1, you are directly take quotient is 1. Otherwise, you take quotient is 0. Okay. Again we take 1. After getting 1, 0, 1, 0. Here initial bit is 1. Again we take 1. Okay. 1 and 1, 1, 1, 0, 1. Okay. Here we are getting the answer is 1, 1, 1, 0. Again we take 1. Okay. Coming to here, first bit is 0. Then we take quotient is 0. Okay. If quotient is 0, what about this one? All zeros. Okay. How to perform the binary division like this step by step. After performing the binary division, you are getting some remainder. Here, what is the remainder here? 0, 0, 1. Okay. This is performed at the sender side. Okay. Here, this remainder is three all these three zeros are replaced by this remainder. Okay. CRC, this remainder is represents the CRC bit. Now send the data along with CRC. Okay. Just these three zeros are replaced by 0, 0, 1. This is at the sender side. Coming to the receiver side, we can perform the binary division for this one. Okay, for the data 1, 0, 0, 1, 0, 0. You have to write in the place of these three zeros, 0, 0, 1. Okay, you have to follow the binary division step by step. Okay, in this binary division method, finally, you are getting some remainder. If remainder is 0, data will be accepted. If remainder is 0 at the receiver side, after performing the binary division, if remainder is 0, data will be accepted. Otherwise, data will be rejected. Okay. In CRC method, first we have to consider data. Depending upon the divisor, we have to choose the CRC bit. Initially, we choose here we have the divisor n plus 1 bits. So that's why I'm taking here CRC bits are n bits. Initially, we put n bits of 0 along the data. How to perform binary division? Okay, after getting the remainder, we can add the data with the remainder at the sender side. We can send the data to the receiver side. Here receiver side, we have to again perform the binary division. Okay, here data plus CRC is presented. Okay, here divisor bits are that will be depending upon the CRC bit. If CRC bits are n, divisor bits are, sorry, divisor has n plus 1 bits, then CRC is the n bits only. Okay, how to perform the binary division as is whatever the procedure we have to follow at the sender side, we have to follow the receiver side. If remainder is 0, data will be accepted. Otherwise, data will be rejected. Okay, if in CRC method, data is represented in polynomial expression. If data is presented in polynomial expression. Here, we have to see here, this one is a polynomial and divisor. Okay. First, we have to choose, here we have the x power of terms. Okay. Here we have to consider each and every x power coefficient. We have to consider the coefficient of the x powers. Okay. Here, first we have start with x power 0, x power 1, x power 2, x power 3, x power 4, x power 5, x power 6, and x power 7. Totally, we are having 8 bits. Okay. Now, how to take the divisor? First, we have to choose this one is represents the x power 0. What is the coefficient here? 1. Next, we have the power is x power 1. What is the coefficient for this one? 1. Next, we have the power is x power 2. For this coefficient, 1. In this polynomial expression, there is no coefficient for the x power 3. Okay, there is no coefficient for the x power 3. At that time, we put the divisor as 0. We consider the 0 bit in the divisor. Okay. In this polynomial, there is no term for the x power 4 also. That's the reason we took another 0. Okay. Here x power 5 is there. What is the coefficient for this x power 5? Only 1. Okay. Next, x power 6 is not there. That's the reason we take the 0. Next, we have the x power 7. What is the x power 7 coefficient here? 1. Okay. If in CRC method, if polynomial expression is there, okay, this is the way to take the divisor. If x power, we have to consider the coefficient for the x powers. Okay, if x powers are there, we have to consider the coefficient for this one. Otherwise, we take the 0 bits in the divisor. Okay. This is the standard polynomial equations. This is one is the CRC 12. Nothing but this is the 12 bit of data. CRC 16, 16 bit divisor. Yeah, ITU. Next, this one is the CRC 30. Okay. In this CRC, if standard polynomials are there, at that condition, you have to consider the coefficients for the x power terms. Next and last method for the error detection method, that is the checksum method. Okay. In the VRC and LRC method, we follow the binary addition. Coming to the CRC, we can perform the binary division. Okay. Last method is the checksum method. With the help of this one, we can detect the errors at the receiver side. Okay. For this one, first we consider the data. If data contains the, if data is divided into the number of sections, if data is divided into the k sections, whole data is divided into the k sections, each and every section contains the n number of bits. In checksum method, what is the first step? Data is divided into the k sections, each and every section contains the n number of bits. Okay. Here we have to show this one at the center side. This section 1, section 2 up to, you have to divide the total data into k sections, each and every section. Now bit of data are n bits only. Okay. Now after dividing the number of sections, you have to perform the, we have to add the year. Yeah, first we have to see the exam. Here, this one is represents the original data. Okay. Now, I will divide this data into 4 parts. And here data is divided into 4 segments. K is equal to 4. Okay. Each and every segment contains the equal number of bits. Means M is equal to 8. Each and every segment contains the 8 bits of data. Okay. Now, how many segments are there? Only 4 segments. Okay. First, we have to see at the center side. Okay. First, we have to consider the first 2 segments. Okay. 1 and 2 segments. Okay. You have to add this one. 1 plus 0, 1. 0 plus 1, 1. 0 plus 0, 0. 1 plus 0, 1. Like that, we have to perform the addition. Okay. If carry extra bit, here you have to observe 1, 1, 1, 0. After adding, this one is a 1, 1, 1, 1, 0. Okay. This one will be added here. Okay. Complement. Okay. Carry will be added here. Okay. We have to perform. After adding, we have to consider one more segment. After getting the result from the 1 and 2 segments, if carry is there, we can add again. Okay. We can add again. Otherwise, no need. Okay. After getting the result, we go for the third segment. Again, we add here. Okay. We can perform the addition. Okay. After getting the results, we can add one more segment. Okay. Finally, we get the sum. That sum is known as a, here, this one is represented as a sum is have 0, 0, 1, 0, 0, 1, 0, 1. Okay. We have to complement this sum for getting checksum. Okay. For getting checksum, we have to complement the sum. Complement is nothing but 0 is replaced by 1, 1 is replaced by 0. Okay. Here, this one is the checksum. Checksum is just complement of the sum. How to get this sum? After adding the segments one by one. Okay. This checksum will be added here. Coming to your receiver side, here we have the first segment. This one is the second segment. Okay. You are adding, after getting this result, we are adding one more segment, that is third segment. Okay. Again, we can add fourth segment. Okay. After adding of this 4 segment, we are getting this one is the sum. Okay. For this sum, we can add this checksum. Whatever the checksum we are getting at the sender side, we can add here. After getting the results of adding up all the segments at the receiver side, we can add the checksum here. Okay. After adding, we get the sum. Okay. We can add all the segments at the receiver side. After getting the results, we can add checksum. Whatever the checksum we are getting at the sender side, we can add the checksum here at the receiver side. Okay, after performing the addition, we are getting some sum. Here sum we have to observe. Here all some bits are 1, 1, 1. All are 1. Okay, we have to complement this one. After complement, all the bits are 0. Okay, if output after complement output is 0, data will be accepted. Otherwise, data may be rejected. Rejected is nothing but errors. Okay, errors can be presented in the data. Okay, this is the checksum procedure. Okay, here we have to show that data will be divided into number of segments. Each segment contains the same number of bits, n bits. Okay, up to here we have the sections 1 to k. Okay, all are having same number of bits, n bits. Okay, after adding this all segments, we get the sum. Okay, we have to complement that. After getting the complement, that bits are again we get the checksum. Okay, sum is complemented. The output of complement is represented as a checksum. Okay, now checksum bits also forward to the receiver side. Okay, receiver side same procedure will be followed. Okay, after getting the sum, we have to add the checksum also. Okay, finally we get the sum. We have to invert the sum. If complement is 0, data will be accepted. Otherwise, data will be rejected. Okay. Same. At the sender side, the date unit is divided into k sections, each of n bits. All sections are added together using 1's complement to get the sum. The sum is complemented and it becomes the checksum. Checksum is sent with the data. Okay. At the receiver side, the unit is divided into k sections, each of n bits. All sections are added together using 1's complement to get the sum. The sum is complemented. If the result is 0, data are accepted. Otherwise, they are rejected. Okay, this is about the checksum. Checksum detects all errors involving an odd number of bits. It detects most errors involving an even number of bits. If one or more bits of segment are damaged and corresponding bit and bits are opposite value in second segment also damaged, the sum of those columns will not change and this receiver will not detect a problem. Okay, thank you. These all are the error detection.